So if you move another 100 micron, you'll be hearing chatter from another community.
Correct.
And so the whole sense is you want to place as many as possible electrodes, and then you're listening to the chatter.
Yeah, you want to listen to the chatter, and at the end of the day, you also want to basically let the software do the job of decoding. Just to kind of go to why ECOG and EEG work at all, right? When you have these local changes, obviously it's not just this one neuron that's activating. There's many other networks that are activating all the time, and you do see sort of a general change in the potential of this like this charged medium. And that's what you're recording when you're farther away. I mean, you still have some reference electrode that's stable, and the brain that's just electroactive organ. And you're seeing some combination aggregate action potential changes, and then you can pick it up, right? It's a much slower changing signals, but there are these like canonical kind of oscillations and waves, like gamma waves, beta waves, like when you sleep, that can be detected because there's sort of a synchronized kind of global effect of the brain that you can detect. And I mean, the physics of this go like, I mean, if we really want to go down that rabbit hole, like there's a lot that goes on in terms of like why diffusion physics at some point dominates when you're further away from the source. It's just a charged medium. So similar to how when you have electromagnetic waves propagating in atmosphere or in a charged medium like a plasma, there's this weird shielding that happens that actually further attenuates the signal as you move away from it. So yeah, you see, like if you do a really deep dive on kind of the signal attenuation over distance, you start to see kind of 1/r² in the beginning and then exponential drop off. And that's the knee at which you go from electromagnetism dominating to diffusion physics dominating.
But once again, with the electrodes, the biophysics that you need to understand is not as deep, because no matter where you're placing that, you're listening to a small crowd of local neurons.
Correct. Yeah. So once you penetrate the brain, you're in the arena, so to speak.
And there's a lot of neurons.
There are many of them.
But then again, there's a whole field of neuroscience that's studying like how the different groupings, the different sections of the seating in the arena, what they usually are responsible for, which is where the metaphor probably falls apart, because the seating is not that organized in an arena.
Also, most of them are silent. They don't really do much, or their activities are, you have to hit it with just the right set of stimulus.
So they're usually quiet.
They're usually very quiet. Yeah. Quiet. There's, similar to dark energy and dark matter, there's dark neurons. What are they all doing? When you place these electrode, again, like within this 100 micron volume, you have 40 or so neurons. Like, why do you not see 40 neurons? Why do you see only a handful? What is happening there?
Well, they're mostly quiet, but like when they speak, they say profound shit, I think. That's the way I'd like to think about it. Anyway, before we zoom in even more, let's zoom out. So how does Neuralink work? From the surgery to the implant to the signal and the decoding process, and the human being able to use the implant to actually affect the world outside. And all of this I'm asking in the context of there's a gigantic historic milestone that Neuralink just accomplished that in January of this year, putting a Neuralink implant in the first human being, Nolan